Hello and welcome to another video. In this video we're going to be working on most frequent prime, and this is going to be the second to last problem from weekly contest 385. And in the problem you're given a matrix, and for every cell you can create numbers in the following way. You can go any path, down, right, up, or left, or diagonal. And when you start, you have to keep going down that path, and you will append digits to this path to the number being formed, traversing. So for example, if you start here and you go right, the digits you'll make will be 1, and then when you come over here, you'll make 11. So you make a new number every single time. So like here, or here, I guess it'll be 1 when you start here, and then once you come down here, it will be 19. And here, you will get 1, you will get 19, and you will get 191. And so basically they tell you can start at any cell, and you can traverse in any direction you want. And out of all the numbers you form, return the count, the most frequent prime number greater than 10 out of all the numbers created. So let's briefly start, let's just look at this example and let's see all the numbers we can create. I don't think we have to do that for every cell, but we'll do that for a few cells. So maybe we'll do it for these 3 cells. So if we start at this cell, all the numbers we can create, let's take a look. So we can go right. So first of all, we can make this 1 just starting here. But 1, we only care about prime numbers greater than 10. So 1 is not greater than 10. So if we go right, we can make 11. If we go down, we can make 19 over here. And then we will make 191. 191. And if we go diagonally, we will make 19. So, and those are the only places we can go because anything else would be out of bounds. So starting at this cell, these are the numbers we can make. So essentially these constraints are small enough that we can just do this for every single starting location. Like assuming this is an m by n matrix, let's figure out the time complexity of that. So it's m by n. So for every cell, we would go in every direction, right? So that there's 8 directions possible, so times 8. And then how long do we have to go in each direction? So it's going to be a maximum of like the bigger of m and n. So if you look at the constraints, m and n are only 6. So this is basically going to be like, worst case, 6 times 6. For every single starting cell, we can go in 8 directions. And then the farthest we can travel is 6. Which will be fine. And then there's one more thing. For every single number we make, we have to check if it's prime or not. So to check if a number is prime or not, I'll get into that, but it's going to be the square root of the number, roughly. Which is fine, because we don't have that many unique numbers. So this will basically just pass doing, you have to recognize that these constraints are really small. So we can just literally try every single starting location, every single number, and then see, get all the primes, and then do that. So the main thing we can talk about in this problem is how to figure out if a number is prime reasonably efficiently. So let's say we have a number whatever number, right? 167 or something. I don't know, maybe not the best number, but let's just pick a number we know isn't prime, right? Let's pick a number what's a multiple of 9 or something? 127. I think that's fine. So let's say we pick 127. So one way to check if this is prime or not is you just start with every single digit, 2 through the number, right? So 2 through 126, I guess. And you just check, is this number divisible by any of these? And if it is, then it's not prime, because, right, a prime number is only divisible by 1 in itself. So we can just loop through these, check if it's divisible. And that would be order n. But we can make this more efficient. We can make it order square root of n. And the way to know that is know that all we need is 2 factors that are non 1 and 127. So that means that if there's 2 factors, let's just think about what's the smallest possible factor a number can have that's not 1. It can be 2. So if one of them is 2, then the other one is going to be the number over 2, roughly, right? So if this is 2 and this is number over 2, that means that one of these factors is going to be less than square root of n, right? And you can do 3 and num over 3 and so on. And so basically you can realize that whenever a number has 2 factors at least one of them will be square root of n or less. Because in order for two numbers to add up, to multiply to be n, you can't have them both be greater than square root of n, right? Like that's not possible. Like if n is like 16, you can't do like 5 times 5, right? So one of the factors has to be here 4 or less in order for this to add up to 16. And you know that, right? Because you have like 2 times 8 or 4 times 4 and so on. So that's the main thing to recognize, because square root of n times square root of n is n. So then if you increase one of them, right? Like if like 4 and 4 are the factors, if I increase one of these, like let's say I increase this, that means this one's going to get decreased. So then the other factor will always be in this range. That's why the only factors we have to check are factors from 2 to square root of n. And that would basically give us, is the number prime or not in square root of n time. So because we can do this in square root of n time, essentially the rest of it is just a brute force. And like, can you code up a brute force problem to go in every single direction possible and get every number? And the way we can also get these numbers is basically kind of straightforward. So let's say we are going down. So we'll start with a number of where we start, like 1. Then we're going to check, is our number greater than 10 and is it prime? If it is, all we have to do is just add it to a hash map, right? So we'll just add it to a hash map, and we'll basically have a hash map of every single prime number we get and its count. So this is not prime, or this is not, well, it's not prime and it's not greater than 10. Then as we add more numbers down the path, it's pretty straightforward. We just take our current number, multiply by 10, and add the digit we're on. So once we're on this digit, let's say we will multiply by 10 to get 10 and add the 9. So we'll have 19. Then we'll check, is it prime? Yes, it is. So we'll put 19 in our hash map. Then for the next digit, we will multiply by 10, add this number, so we'll get 191. Check if it's prime. Not really sure about that one, but if it is, we'll add it to our hash map. Then basically we end up having a hash map of primes and counts. You can either have a hash map of all your values or primes and counts and check if they're primes later. But either way, then it's pretty straightforward. You just go through your hash map and you just get the prime number with the biggest count. And then you just return that. I think that's what they asked for, right? Yeah, prime number with the greatest frequency. So this is basically just as straightforward as it gets, just brute force. Can you figure out if a number is prime? And honestly, I think even if you do the prime in O of n, it'll still pass just because the constraints are pretty small. So if you think about it also, like how many unique numbers and stuff you can have. So worst case scenario, your matrix is 6 by 6. So I don't think I have a 6 by 6, but let's say our matrix was 5 by 5 worst case and not 6 by 6. There's not many ways to actually get a 5-digit number here, right? Like this is one way, this is one way, this is one way, this is one way, but there's not too many, right? You have to like start at one end, complete end, and go to another end. So from each end, you can only go to like 3 other ends. So there's only like 12 or something ways to get 6-digit numbers. And then there's like more ways to get 5-digit numbers and so on. But what I'm saying is like the numbers aren't going to be that big. So there's not going to be like that many total numbers. Like you're not going to have like 10 to the 6 numbers or anything. You'll have like significantly less. And so because you'll have significantly less numbers, then for each number, it's a square root to figure out if it's prime. We're going to be able to have that work. I guess maybe it'll fail. I'm not sure. We can try it without the square root and see if it fails or not. But that's the basic idea. You literally just brute force, get every single number possible, check if it's prime, maintain a count, return the count. So we can look at the code here. So I just made an easy function that checks if a number is prime. I'll link my prime factorization video that goes into this a lot more detail. So we'll try from every factor up to the square root of the number. And then if any one of those is a factor, then it's not prime. Otherwise, return it is prime. Then we just have like a billion for loops. So we loop through every single cell here, and we loop through every single direction we can go. So the directions we can go, if you think about it, are, so horizontally, we can either go back or stay in the same cell or go forward, which means we can either go -1, 0, or 1. Vertically, same thing. We can go up. We can stay in the same cell or go down. So -1, 0, or 1. So essentially, we just loop horizontally through all the states and vertically through all the states. And the only one that's invalid is if you don't move in either direction. Then we just get our number. And we keep, like I said, we keep going in the direction we picked. And to get our next number, we just multiply our number by 10 and add whatever cell we're on. And we keep doing this until our cell is out of bounds. Then we check, is our number greater than 10? If it is, let's increment the count. And so it looks like I checked for primes after I have the dictionary. You can do it either way. And then you just update your row and your column based on the direction you're going. Then once you have all your numbers, so this isn't necessarily only prime numbers. I guess I stored every single number greater than 10 and its count. Then I just say, okay, count is 0, results -1. Let's go through all our dictionary values. If our key is prime and our count is greater than it was before, then let's update it. And also, I believe they told you to, if there's a tie, return the biggest number. So let's take a look. Yeah, if there's a tie, return the biggest number. So pretty straightforward. So I just said if the value equals my highest count, then let's just take the biggest number out of the two. So check if it's prime, then check the count, and if the count is better than it was, just update the value and update the count. So that part should be pretty straightforward, right? You just have a hash map of numbers and how often they occur. Check if it's prime. If it's prime, then check if the count is higher than it is before, and then just return the prime number with the highest count. And so we can submit, and it's pretty good. So yeah, we can actually test this out of my curiosity to see if it would fail if we literally tried if we tried like a no-event solution. So here, this would be num. So let's try this. Looks like it might fail. Nope, it passed, but you can see the difference is significant. So just have to know that for prime numbers, this is the better way to do it. Yeah, because obviously you don't want like 9,000 runtime. And I will link my prime factorization video, which talks about like how to get efficient prime factorization of a number. So yeah, and hopefully that makes sense to you why you only have to go to the square root, because one of the two factors will always be the square root or less. And yeah, that's going to be all for this one. So we can briefly do the time and space. This one's going to be kind of weird for time and space just because you do like a loop, infinite loop. So we have row, so n times 8, which I guess is basically constant time. And then it's also going to be times like another side to go down this diagonal. So it'll be like n times m times n again or something. Like n times m times like max of like n and m or something like that. And then so we do all that. And then to go through all the numbers, we have to check if they're prime. Not super sure how many numbers there are. I know it's not too bad, but essentially that would be like p square root of p, where p is like all the prime numbers we have. Square root of p, something like that. It's super hard to calculate like exactly for this one just because there's like so many things. So this would be like plus or something like this. And for the space, so what are we using here? So once again, we have to kind of know how many unique prime numbers we have, which is kind of hard to say. Yeah, I mean, you can try to figure it out. Like it would be roughly like n times m times this whole thing, I guess. I think it would be like n times m times this, something like this is how many like prime numbers you can have. Because for every starting cell, you can get like 8 numbers, or not 8, but like a dimension of numbers. So it'd be around this, which like I said is totally fine. That's like 6 times 6 times 6, which is fine. Like that'll easily pass. So this is going to be like, I guess we can write that here. So we can write like n times m times this. So really, I think our actual complexity is like, this will be how many prime numbers you have. And then we multiply this by like square root of this whole thing. So it'll be something like this. I think is probably correct. But yeah, this will easily pass because like, this is like 6 times 6 times 6 times square root of that whole thing, which is like easily going to pass. Maybe there's like another dimension in here because there's also this 8. And you saw that like not having the square root does make a difference, which makes sense. Because if this number is like 1,000 even, 1,000 times 1,000 is gonna not pass. So this has to be below 1,000. So that's why it makes sense that it's that's why it makes sense that it barely passes, right? Like 6 times 6 times 6 is still like 200 or something, which is like reasonably big if you multiply it by itself. Or yeah, there might, like I said, there's also these 8 sides, so it's more like 6 times 6 times 6 times 8 times like 6 times 6 times 6, which will get pretty big. So that's why this square root, kind of useful, good to know. And like I said, I'll link that video. And yeah, it's gonna be all for this one. So hopefully you liked it, and if you did, please like the video and please subscribe to the channel. And I'll see you in the next one. Thanks for watching.